An introduction to the ideal gas law, otherwise known as PV equals Nrt. The combination of laws above, referring to the gas laws that we have discussed previously, leads to the formulation of the ideal gas law. Most gases obey this law at temperatures above 273 K and at pressures of 1 atmosphere or lower. Now let's just remind ourselves before we go on to the universal gas constant of what each of these represents. P represents pressure, V represents volume, N represents moles of gas, R is the universal gas constant, which we'll talk about in a moment, and T is equal to temperature, which will need to be in Kelvin. Now R is the universal gas constant, and all of these gas constants are listed on your AP reference table. Which gas constant you use really depends on what variables are included in your word equation as you use PV equals Nrt. What pressure are you using? Are you using atmospheres? Are you using torr? What volume are you using? Most of these are listed in liters. Do we have moles? Do we have joules? It really depends on what is involved in the word equation to which gas constant you're using. This equation is useful because it can be manipulated to include other variables. For example, N, or the number of moles, can be replaced by molar mass and then manipulated further to include density, and we'll talk about that in a little bit. In addition to the ideal gas equation, other equations can be derived. So let's talk about PV equals Nrt. And let's say I have an original situation with my gas. I will make all of these P1, V1 is equal to N1, R1, and T1 as my initial situation, and then P2, V2 equals N2, R2, and T2 as a final situation. If I work with these, I can set these two situations equal to each other by basically saying, hey, all the units are going to be the same here, so R1 is going to be equal to R2. And if R1 is equal to R2, we can take this a step further and cancel these R's because all the units are going to be the same and make P1 V1 over N1 T1 equal to P2 V2 over N2 T2. Now as we do this, we can derive different gas laws. So let's say that we have a situation where we're holding the number of moles of gas constant. If we hold the number of moles of gas constant and we remove the n's, all of a sudden we have the combined gas law, as P1 V1 over T1 is equal to P2 V2 over T2. What if we had the number of moles of gas held constant and also the moles of pressure held constant? If that was the situation, then we'd have V1 over T1 is equal to V2 over T2. And in that situation, we'd have Charles' law. So if you see a situation where pressure is constant and the number of moles are held constant, you have Charles' law. Let's look at a different situation. What if we had the number of moles held constant and the volume constant? So now we have P1 over T1 is equal to P2 over T2. In that particular situation, we would have Gay-Lussac's law, which looks at a direct relationship between pressure and temperature. What if we were in a situation where pressure was held constant and temperature was held constant? In that situation, we'd have V1 over N1 is equal to V2 over N2. In that case, we would have Avogadro's law, which looks at the relationship between volume and moles of gas. Finally, what if we had a situation where the number of moles of gas is held constant and the temperature is also held constant? In that situation, we'd have something very familiar, which is P1 V1 is equal to P2 V2, and that would give us Boyle's law, P1 V1, and looking at the inverse relationship between pressure and volume. So the big idea here is that if you know PV equals Nrt, which is on your reference table, and you set the two gas constants equal to each other in two situations, such as an initial and final, you hold different variables constant, you can pretty much derive any one of these gas laws as needed. So if you know which variables are held constant, any gas law can be derived. Let's see some examples of the ideal gas law problem. A sample of nitrogen gas kept in a container of volume 2.3 liters and at a temperature of 32 degrees Celsius exerts a pressure of 4.7 atmospheres. Calculate the number of moles of gas present. So the first thing we're going to do is write our formula. PV equals nRT. When we look at this, we see that the volume is 2.3 liters, so that's going to represent our V. Our temperature is 32 degrees Celsius. We're going to need to convert that into Kelvin. And we have 4.7 atmospheres. So my P here is going to be 4.7 atmospheres. My volume is going to be 2.3 liters. I'm solving for moles of gas. The R that I'm using here is going to be 0.0821, and that is liters, atmospheres over Kelvin mole. And I'm doing that on purpose because we need to see how these units are going to cancel. And finally, 32 degrees Celsius converted into Kelvin is going to be 305 Kelvin. So when we work this out and we solve for N, we can see that this whole unit right here, sort of crossed out my N there, whoops, whole unit right here is going to go on the bottom below atmospheres and liters. So when I rewrite this, I'm going to have the following. When I look at this, I can see what units are going to cancel. So atmospheres will cancel atmospheres, liters will cancel liters, temperature will cancel temperature, and the moles right here will flip up and be the unit that we're looking for at the end. So if I do all these calculations and I solve for number of moles of gas, I find my number of moles of gas to be 0.43 moles, which is to the correct number of significant figures. Let's look at another example. Given that 6.9 moles of carbon monoxide gas are present in a container of volume 30.4 liters, what is the pressure of the gas in atmospheres if the temperature is 62 degrees Celsius? The first thing I'm going to do is write the ideal gas law. PV equals nRT. So I'm solving for the pressure of gas. So P is going to be my unknown. Volume is 30.4 liters. The number of moles of gas is going to be 6.90 moles of gas. The gas constant that I'm using is the one that's going to go with atmospheres, liters, and moles, and Kelvin. So that's going to be 0.0821 liters, atmospheres over Kelvin mole. And then finally, my temperature is 62 degrees Celsius, which is going to be 335 Kelvin. And again, what we can see here is that Kelvin cancels Kelvin, moles cancels moles. When I bring liters over here, liters will end up canceling liters, and I'll end up with a pressure in atmospheres. So if we solve this and we solve for pressure, we find that the final answer is going to be 6.24 atmospheres. One final problem. What would the pressure in torr be of an ideal gas of a 0.17100 mole sample occupied by a volume of 3,050 milliliters at a temperature of 779.9 Kelvin? So PV equals nRT. I am again solving for pressure. That is going to be in torr. I need to change my milliliters into liters. My gas constant corresponds to liters. So for my volume here, it's going to be 3.05 liters. That is a must do. For moles, I have 0.171 moles. I am using a different gas constant here. I need to use the gas constant with torr. So that's going to be 62.36 liters torr over mole Kelvin. And then finally, at least they give me the temperature in Kelvin. So that is 779.93 Kelvin. Again, it is always good to double check to make sure you're using the correct gas constant by canceling. So Kelvin cancels Kelvin, mole cancels mole. Ultimately, if I was to bring the liters over on the bottom here, liters would cancel liters, and I'd be left with the pressure of torr, which is what I want. So if I solve for pressure here to the correct number of significant figures, which looks like it's going to be 4 significant figures, I should get 2,726, well, I could put 0.8 torr. Actually, it's to 5 significant figures. So my answer is actually right. Look, 5, 5, 5. It's almost like I planned it. So the final pressure here is 2,726.8 torr using the correct gas constant. So there you have a little overview of how to use the ideal gas law.